Hello. In this video lecture, I will be covering Chapter 6, Module 6. The title of the chapter is Circular Motion and Gravitation. I hope you will find it interesting. We will begin with the study of circular motion, and then we will apply what we studied in circular motion to the theory of gravitation. When we talk about gravitation, basically you are thinking about things that are orbiting each other, such as the Earth around the Sun, or a satellite going around the Moon or the Earth, or something like that. So all of that, of course, is within the study of circular motion. Okay. So the circular motion, when you think of the term circular motion, think of one object going around another object, but the other object we will assume that it is stationary. In other words, it's too heavy and to be influenced by the smaller object that is orbiting about it. For example, take the motion of the Earth around the Sun. So here is if we assume it's a circular orbit, so here is the Earth going around the Sun like that. Here is the Sun right here. And this is the radius between them, and the Earth goes around it, where this is the velocity or the speed of the Earth. As you can see here, the velocity vector, this vector here, constantly changing. In other words, when the Earth is here, the velocity is like that. When the Earth is here, the velocity is in this direction, and so on. As you can see here, the velocity vector is constantly changing direction. It's tangential. It's tangential to the circular path, and as you can see, it's constantly changing direction. If you remember, if you have a motion that is constantly changing magnitude or direction or both, then you will have an acceleration. Okay, so here maybe the Earth is going around the Sun, say with constant speed, let's say 1,000 miles an hour, and I think that's the correct number, approximately, about 1,000 miles an hour. But however, it is constantly changing direction, as you can see here, because the velocity is tangential to the circular orbit. So, and this direction is constantly changing, and therefore you would have an acceleration. And that kind of acceleration we call the centripetal acceleration. Acceleration. Your book, for now, he calls it radial acceleration. Okay. Later on, we're going to use this term. But anyway, this is called centripetal acceleration. What's the direction of the centripetal acceleration? Well, let me draw it again for you. So if the Earth is right here, here is the Sun. Let's just make it a point. And that's the radius, or the distance between them. The centripetal acceleration is always pointing toward the center. The word centripetal, it means in Greek, I believe, center-seeking acceleration, center-seeking. Or, in other words, it is always directed toward the center. So that's the centripetal acceleration. I like to call it A sub C. Your book calls it A sub RAD for radial, okay, radial, because it's along the radial direction, the radius. I like to use the notation A sub C, so I'm going to stick with mine. Okay, so here is the centripetal acceleration, and there is the velocity of the Earth, you know, at this instant. And the way they are related to each other is that the centripetal acceleration is equal to is equal to v squared over the radius. Okay, assume that this is the radius of the orbit. Okay, this is a very important formula. So the centripetal acceleration is v squared over the radius of the orbit. Got it? Okay. Now we know that from Newton's second law, F is equal to ma. So in this case, you know, whenever you have acceleration, there will always be a force associated with it, and the converse is true. Whenever there is a force, the motion, if the motion is not static, it's not zero, there will always be an acceleration associated with that, and that acceleration, for this matter, since ours is centripetal, so we refer to this force as also centripetal force. And it is also directed toward the center, So it's basically going to go also like that. This is F sub c. So in other words, let me make a bigger circle so I have a better picture. So here is the Earth, or anything that is going around. Here is the radius. So you have here two vectors where, don't worry about the length of the vector. I'm kind of not, it's not important for now. So let's just say this is F sub c and this is A sub c, instead of saying. So they both in the, that's why we refer to this force as a centripetal force, which means what? It's a center-seeking force. Just like a center-seeking acceleration, we have a center-seeking force, okay? And again, the velocity is always tangential like that. This is the velocity. Got it so far? Okay. So with this in mind, so for now, we have said F equals ma, cc. Let me just put cc to remind you this is centripetal. And then we said that A sub c is equal to v squared over r. So in this case, the force in this case is going to be m v squared over r. Okay, I'm going to box this equation because it is important. All right, now what about the velocity? Let's say, is there a way that I can find it? Well, think about it. If you have an object that is going around another object in a circular fashion like that. So here is the radius of the orbit right here. Let's make it big R for now. And here is the object. It's moving in this direction like that. And I would like to know the speed of the object v. Okay? Now, one way to do that, and I believe we covered this a little bit, and basically we know that the speed is distance over time in its simplest form. So in this case, the distance traveled by the object, if I take the full circle, here, whoops, get out of here. If I take the full circle here, it's basically the circumference of the circle divided by the time it takes it to complete that circumference. And we refer to this time as the period. Remember, I don't know if you know, I don't remember if I covered it or not, but the term period, it means time to complete one cycle, okay? One cycle, or one circle, one orbit, you know, whatever it is. So, or one wavelength. Okay, so the period is the time to complete one cycle. And the cycle for our case here basically is a complete orbit, or complete circular circle. You see what I'm saying? So here we can say that the velocity for our case, the distance here would be the circumference, 2 pi r, divided by the period. And I like to use the symbol, the Greek letter tau for period. Your book uses capital T, which I don't like because T is reserved for tension. Remember that? We did some problem with tension. And I don't like, so I'm going to avoid the capital T. Your book uses capital T for period. I like the Greek letter tau. Okay? So that's another equation. So now I have with those two, I can combine them together if I want to. Let me just show you how they combine together. In other words, if I would take the velocity, which is v equal 2 pi r over tau, and I take that and plug it right in there, okay? So in this case, F sub c is going to be equal to, well, hold on. Let me just first square it, sorry. If I square both sides, it's going to be 4 pi squared r squared over tau squared, and then I'm going to plug it back in the force equation. So that's going to be m over r. You know, I'm changing the variable r to capital R here, times v squared, which is 4 pi r squared over the period squared. One of the r's cancel out here. I don't know if there is anything else. So therefore, the centripetal acceleration in this case is going to be 4 pi m r over the period squared, tau squared, okay? That'd be one version for that. All right, good. Let me do some problem before I move any further than that. There's just maybe too many equations to handle. So let's see how they apply. So back to the book here. I'm going to do example number, let's start with number 1. I'm going to do a bunch of examples from the book, and then I'll do a couple of problems from the homework. I'll start with example number 1. Let me show it to you. on page 155. Right here, let me make it bigger. There we go. I hope it's big enough for you. Okay, it says, I'll start from here. It says, suppose you fly a propeller-driven model airplane. All right, so I'm going to fly an airplane right here. Airplane on a 5-meter string in a horizontal circle. So this is a horizontal circle, okay? Basically, you are whirling it above your head, if you will, okay? So it's a horizontal circle above your head. And here is the plane. Remember, your head is right here. The top of your head is right there. So, and the radius of that orbit or the circular path of the plane, that toy plane, is 5 meters. You got it? 5 meters is about 5 yards, right? Okay, the airplane, which has a mass of half a kilogram, which is about a pound, flies level and at a constant speed and makes 1 revolution every 4 seconds. Now that's an interesting statement. 1 revolution every 4 seconds. I'll come back to it. How hard must you pull? How hard must you pull on the string to keep the plane flying? Okay, so what is he asking for? Well, whenever you are asking for a force toward the center, okay, remember we said what is the force toward the center? It's the center-seeking force, centripetal force. So basically he's looking for F sub c, the one we are just dealing with. So when he said, how hard must you pull on the string to keep the plane flying in a circle, basically, what is the centripetal force that is associated with that? Okay, given the radius 5 meters, the weight, the mass of the plane is half a kilogram, and I want it to take to make 1 revolution every 4 seconds. What is that? That's the period. You agree with me on that? So makes 1 revolution every minute, 1 cycle per second or whatever. So that would be the period, correct? Okay. He says, how hard must you pull? So basically, he's looking for that for the force. Okay. Need to switch back. I forgot how to switch back. Oh, there. All right, there we go. So we have here so what I have here is a picture. Always draw a picture. I keep saying that. And here is the plane right here. Here is the radius, if you will. Here is the plane. And this is the velocity right here. I don't know the velocity. He didn't tell me anything about the velocity. All he said is that it makes 1, I'll put it in numbers, 1 rev per 4 sec. Okay, he gave me this information. I'll come back to it, which is basically the period. I hope you know that by now. And this is the radius right here. And the radius, I'll make it capital R. Capital R, what is this equal to? 5 meters, right? And he said the mass of the plane is 0.5 kilogram. And he's asking for the force. How much must you pull this way? That's the force, okay? So we know that the centripetal force is equal to, again, I can just basically use this whole thing and I'm done with the problem. I got everything. You see what I'm saying? So I can just use that and I'll be done with it. But let me just work some details. Let's assume that I would like to know the speed of the plane, okay? We said that the speed, look at that, here it is, 2 pi r over tau. You see what I'm saying? So I can just say so before I do the force, hold on, we'll come back to the force in a sec. So let's find the speed. The speed is 2 pi r over tau. What is tau? Well, tau is the time to complete 1 cycle, okay? And that time is equal to 4 seconds. See that? So in this case, so that will be 2 pi times 5, the radius is 5, divided by 4. And I just need to calculate that. I hope you're calculating with me. So that 2 pi, 6.28, times 5, divided by 4, answer 7.85. So I have the velocity 7.85 meters per second. There we go. And if I want to know what is the acceleration, so let's say centripetal acceleration, well, that just v squared over r. So 7.85 squared over the radius is 5. So I can calculate that as well. Divided by 5. Answer 12.3 meter per second squared. You see what I'm saying? So A sub c is 12.3 meter per second squared. And finally, he wants the force. Well, it's just ma sub c. I can use that. So saying, I mean, the mass is given to me. The mass of the plane is 0.5 kilogram, and A is 12.3. Answer 6.16 Newton. Now, of course, I've done a lot of steps that maybe they're not necessary. Or I can go directly to this formula right here, plug in everything, and it should get the same answer. You see what I'm saying? But anyway, I just wanted to work out the details, show you how to work those formulas that we have just covered. All right, another cool example, 6.2. This one is a little bit harder. It says, here we go, look at the circle. It's a horizontal circle, and then you have this, you have a string and a ball, and you're going around in a circle like that, okay? So here says a tetherball, which is right here. A tetherball is attached to a swivel in the ceiling by a light cord of length L, here is the L right here, as measured from the ceiling to the center of the tetherball. When the ball is hit by a paddle, it swings in a horizontal circle with a constant velocity v. Okay? Remember, we say constant speed, not constant velocity, because it's changing direction. So the velocity is not constant, but the speed is. You get that? All right. And the cord makes an angle beta right there with the vertical direction. The ball goes through one revolution in time tau. We'll just call it tau for now, right? Not t. Okay, so that's basically, he gives you the period tau. Assuming that tau and mass m and the length L of the rope are known. So let's say that these are numbers. Derive an algebraic expression for the tension F sub t in the cord and the angle beta. Okay? Well, let me show you what he's talking about. And I am not, like I said, I don't use the notation that he does. I don't use this notation, F sub t. I just go T for tension rather than F sub t. But anyway, let's see how we can solve this problem. You know what? Hold on. Let me maybe move it to the side so you can probably see the picture. I guess like that. I think it's going to leave the video screen on the side. I'm not sure. Anyway, here it is. There we go. Okay, so we have here example 6.2. And what I have, let me draw the picture for you. So what I have, here is a circular path. And here is the ball right there. Here is the ceiling here. And that is the ball right here. Okay. And let's assume the ball is moving in this direction. Here's the radius of the ball, the radius of the circular path, R, capital R. Here's the length L, and that's the angle beta. Okay, there we go. We have something like that, and of course we have the mass here, m. Okay, that's basically what the picture looks like. Now we're going to be using stuff that we have studied from chapter 5, application of Newton's law, because we're going to be using forces here. The question is, what is the centripetal force? Obviously, the force, the tension in the cord here, let me make it a solid line. The tension in the cord here obviously is not the centripetal force. Why? Well, because it's not toward the center. See, in order for a centripetal force to be centripetal force, it has to be toward the center. And the center of the circular path is right here. The force in that, in other words, have to be in this direction. Well, there is no force in this direction. This force, the tension, remember tension out of the body, so it's just going to be like that, upward. You see what I'm saying? Then you get the weight of the ball downward this way. So what's going on here? Do you see the difficulty of the problem? The centripetal force have to be toward the center. Got to be toward the center. And so far, I don't see that centripetal force. So what's going on here? Well, hold on a minute. That's why I want to solve this problem. So what I want to do now, I want to draw the free body diagram. So I'm going to take only the string and the ball right here. Here's the ball. Here's the string first. Here's the ball. And I asked the question, what are the forces on it? Well, I got the mg of the ball. And I have the tension, right? You know, the stuff that we studied back in chapter 5. There we go. And of course, this angle here is beta. That makes it right here. Beta. You know, alternate angles. Now, with this in mind, let me change the color. With this in mind, now I can resolve things into components. Remember, I have x and y components here. So here I'm going to have t sine beta, and I have t cosine beta, and everything else is fine. So now, with this in mind, now watch what's going on here. Let me ask the same question I asked a minute ago. Do we have a centripetal force? And the answer is yes. This component of the tension is toward the center, right here, okay? And this component of the tension plays the role of the centripetal force. Now, if there were two of them, well, both combined play the role of the centripetal force. If they were opposite, we'll subtract them. Both combined, they play the role of the centripetal force. Any vector that is toward the center or away from the center, okay, if it's away, you mean it's a negative vector. So if all these vectors that are toward the center will play the role of the centripetal force. So we have one vector. You see what I'm saying? So now I can say, all right, so I'm going to use x and y component here, just like my datum right there. So I'm going to have, let me put them here. Sum of the force in the x direction is equal to ma sub c, because the interesting stuff is happening along the x-axis, and there is a motion. So what are the forces in the x direction? Well, there is only this, minus t sine beta equals ma sub c. I'll come back to it in a sec. Sum of the force in the y direction, what do I have? I get the t cosine beta minus mg equals 0. You see that? 0. Why 0? Well, because there is nothing going on in the y direction. I just have two forces, right? So here's going to be t cosine beta minus mg equals 0. And of course, with this equation, I can solve for t, because I'm interested in finding that t. So I move the mg to the other side, and I divide it by cosine beta. And there we go. I have an expression for the t. Got it? All right. Now, go back to this. I started with this equation right here. I want to work with this equation, yes. So I'll call it star. So now, back to star. So I have minus t sine beta equals ma sub c. I forgot what he's asking for. I'm sorry. He's asking for the tension. Is that what he's asking for? Assuming derivative algebraic. Yeah, for the tension. Okay. Well, I got the tension right here, but let's make it a little bit better. All right. So I have that. Now I'm going to take this and plug it in here. Okay. I mean, hold on. Let me just stop here. He said find an expression for the tension. I believe this is it. I have already answered his question. This is the answer right here. I'm done, really. He said find an expression for the tension, because he gave me the mass, the g, and the beta. So there we go. Here's the tension. But let me go a little bit further. Okay, let me just go one more, just a little bit further. Let's say, for example, I want to find, let's say, let's say I want to eliminate the angle, okay? Let's say I want to eliminate the angle, the sine and cosine, okay? Let me just keep going further with it. So what I have in here is t sine theta. Now, let's say I want to get an explicit expression for a sub c, okay? I want to keep this t right here. So in this case, I'm going to have minus t sine beta equals m v squared over r, right? Okay, and we said that v is equal to 2 pi r over tau. And he gave us tau here. Didn't he mention something about tau? I believe he did somewhere. Let's continue on. There we go, the time t. I'm sorry, yeah, this is the time t, so the tau. There we go. Yes. Okay. So now I wanna plug it back into my equation here. Let me just square them together, square both sides. So that's going to be 4 pi squared r squared over tau squared. Now plug it back into my equation. So I'm going to have here minus t sine beta equals to m times 4 pi squared r squared over r times tau squared. Clean up things so the r's cancel out like that. And if I work it out, I'll end up with t sine beta equals, with a minus. The minus is not that important, simply because I could really go back to the graph. See, I could make the graph going from here. In this case, t sine beta will be on this direction. It's going to be positive. So here the minus sign is not really terribly important. Instead of saying it's really arbitrary. So maybe I should, I'm trying to erase this thing. So maybe I should just cancel it, ignore the minus sign for now. So let me just ignore it because it's not important for our case here. So ignore minus sign. So in this case, I'm going to have t sine beta equals to, and what am I left with? 4 pi squared mr over tau squared. Okay? All right, moving on. However, look at this. Okay, let's suppose I want to get rid of beta, because look, he says here, derive an algebraic expression for the tension in the chord and the angle beta. Okay, so in terms of what? Assuming in tau, m, and l. So basically, I want to eliminate beta. Okay, so what I want to do here, I want to find a way to eliminate sine beta somehow. Okay, how do I do that? Well, let's go back to the diagram. Look at the diagram here, or let's say this one here. Okay, so here we have. Let me draw this triangle at the bottom of the page, and I'll show you what I'm trying to say. Here it is. Here's the triangle. This is the length L. This is beta, right? And this is the radius R. So notice that L sine beta equals R. See what I'm saying? In other words, I can take this and plug it right in there for the R. So in this case, it's going to be t sine beta equals 4 pi squared m over tau squared times L sine beta. Why did I do that? Because I don't want the sine beta. See, that's just gone. And so that will cancel out. It's just a little trick. It doesn't work all the time. It just happened to work this time. Okay? But it's kind of an interesting one. So therefore, he said find an expression for the tension. I take it back. This is an answer, but he wanted without the sine beta. I didn't read that very carefully. Sorry about that. He said here he wanted it in terms of the tension, period, mass, and length for the tension and for the angle. So we're not supposed to put that beta in there. So anyway, so this one is okay, but this one is definitely what he's looking for, this expression here. So that in this case, the tension will be 4 pi squared ml over tau squared, and I think this is what he's looking for. See what I'm saying? I'll look up his, well, let me look up his answer, make sure that I am doing it right. Tension, there it is, right here. I think so, yeah. This looks pretty similar. Yeah, this is basically what he's looking for. All right, the second part, he says, what is the angle, you know, beta or cosine beta in terms of the variable that are given to us. In other words, take this, plug in the value of tension, solve for cosine beta, and that's it. That's basically what he's asking for. So, okay, so let's keep that in mind. So we have the period is equal to mg over cosine I'm sorry, tension, excuse me, tension equal to mg over cosine beta. So in this case we will have, so here we have from sigma fy equals 0, and that will be equal to the tension equal to mg over cosine beta. Solve for cosine beta. This will be mg over the tension. And the tension, of course, is given to, we have just found it right there. So therefore, cosine beta is equal to mg over 4 pi squared ml times tau squared. The masses cancel out, and therefore cosine beta is equal to g tau squared over 4 pi squared L. And I think this is what he's looking for. There we go, right there. G tau squared 4 pi squared. Okay? That's basically what he's looking for. All right, good. The next problem that I want to do is example 6.3. Which is right here. So basically what you're looking at in this picture, you have a car. Let's say you are driving down the highway, so you are going, you know, let's say northbound, and now you're making a turn toward the east like that. So you're making a turn like that. So, and he's asking for something. He says, in this example, the friction force. Of course, you don't slide out because of the friction force. The friction force between the vehicle's tire and the road provides the radial acceleration. Basically, what's cool about this example is that the friction force plays the role of the centripetal force. You'll see it in a second. It's that a car rounds a flat, unbanked curve, okay, with radius big R. If the coefficient of static friction between the tires and the road is mu sub s, derive an expression for the maximum speed at which the driver can take the curve without sliding. And then the second part is easy. You just kind of plug in the numbers that you've gotten from part A. Okay, I'll give you the radius of the street, of the curve, whatever you call it, and then you have the static friction 0.9, and then we'll plug it in. But anyway, this is how it works. Let me show you. So what you have here is the, let's say it's a top view or a bird's eye view of the whole thing. So here is the curving road. Here is you right here driving. Okay, and let's say here is your velocity. It's always tangential to the curve. Remember that. And here is the radius of curvature. So the radius is right here, roughly. Okay, that's the radius. And of course the centripetal, well, I'll come back to the centripetal in a minute. And there we go. And this is your velocity and so on. Okay, what's given to us? Well, he says that you are going around and there is a static friction there that will give you the, that will allow you to do the maximum velocity. So what are the forces on the car? Now, if I look at the car from the street view, this is the top view. What you're looking at here is a bird eye view, a bird in the sky, and it's looking down, and this is what it's seeing. But on the street view, let's say a police patrol is looking at you, he's going to see you. Here's your car. All right, there's the steering, here's you right here. You're driving towards the police patrol, right? So what's happening here? Well, what are the forces here? Well, you get the force of mg, the weight of the car and you and everything else in the car, and then you get the normal force n, right? There we go. As the car going around, you know what I mean? So in this case, this is the y-axis, so this is really the y component right here. So y component. So in this case, sum of the forces in the y direction is 0. The car is not going up and down, of course. So n minus mg equals 0. And I think we've talked about that last week. So n equals mg, which is cool. Let me just box that, and I'll come back to it in a sec. Now back to the bird's eye view right here. So this is the top view. What's going on here is, let me eliminate the radius for now. Here's your, oops, trying to make it better. There we go. Okay. All right, so here is the radius. I'm sorry. Here's the radius right here. What's happening? What's forbidding you from not sliding out like that, okay, is because there is something is pulling you toward the center. Make sense? And that something that is pulling you to the center is basically the friction force. You need to think about that if you don't get it. But it is the friction force that is playing the role of the centripetal force in this case. Okay? So in this case, if I assume this is the x and y, if you will, this is the x direction right here. So in this case, sum of the forces in the x direction is equal to ma, a being the centripetal acceleration. So here the force is basically the friction equals to mv squared over the radius of the curvature, or the road. Okay, that's the velocity right here. Now we know that F is equal to, F is equal to mu n, but as you can see from here, n is equal to mg, so F is equal to mu mg. Now to get them, he said, what is the maximum velocity that you can go without sliding? Well, the maximum velocity remember the ms is always greater than m sub k, the kinetic friction. So the maximum velocity is that when the mu value is actually the static friction, m sub s. So that will give me the maximum, gives V max, maximum velocity. Got that? So now I go back to this formula here. And this is the value of F right there. You're going to plug it in here, this one. You put it right there. And then you just solve for the velocity. It becomes max. In other words, this becomes mu sub s mg. This will give me mv max squared over r. Masses cancel out. And therefore, V max is equal to mu s g r under the root. You see what I'm saying? And that's it. We just plug it in. We plug in the values he gives us. He said 0.9 for mu sub s. Let me go back to the problem. 0.9, the radius is 250 meters. 9.8 times 250 meters. And then you just calculate that. That will give you the maximum. I think I have it. Let me calculate very quickly. So in this case, I'm going to have that. Answer 47 meters per second. That's a lot of, that's a very high speed. You're talking here, over 90 miles an hour before it slides down. That's the maximum velocity you can go on that road. You see what I'm saying? Okay, good. The next, oh, by the way, example example number 4. This is 6.3. Let me show it to you. It's basically similar to 6.3, except that the road, look at that, it's banked. In other words, there is an angle to the road. You see that? There is this angle, and it becomes a little bit hard problem. I am not going to do this problem, and do not expect a problem like this to be on the exam. I don't think I have any of the problems like that. They call them a banked curve, okay? So I'm not going to be covering banked curves. A little bit tougher. From my experience, a lot of students get confused with those kind of problems. They're a little bit hard, and I don't think you need them. So we're not going to be covering banked curve like that with an angle. All right, so you can ignore that. All right, the next topic, or the last topic of this chapter, is gravitation. So let me go over that very quickly. I hope you'll find it interesting. And I think, let me look up what section is that in the book. Oh, here it is. Newton's Law of Gravitation. That's section 6.3, page 161, to show it to you. Right here, Newton's Law of Gravitation begins here. Please take the time to read it. All right. In its simplest form, here is the meaning of it. Basically what it says, if I have two masses, say the Earth and the Sun, or the Earth and the Moon, even you and the calculator in front of you, any two masses, okay, any two masses at all. Here's one mass, here's the other mass, and let's say, let's call this mass 1, mass 2, and let's say the distance between their centers, I'll call it R, then there will be a gravitational pull between them, okay? This gravitational pull, it's a force. Pull means force, right? This gravitational pull is equal to the product of the two masses divided by their distance squared up to a constant g. We call that g is the universal gravitational constant. The universal gravitational constant. Okay? And it is equal to 6.67 times 10 to the negative 11 Newton meter squared over kilogram squared. Okay? So just a constant value. In advanced physics, there is a lot of meaning to this number, but we're not going to go over that here. Okay? So that's just a constant. It's called universal gravitational constant. That's basically the story. Now, the thing is, all masses gravitate. Any mass you can ever think of, whether your mass, the mass of the calculator in front of you, the mass of your computer screen in front of you, the mass of your pencil, anything around you, okay, gravitates. What that means is that there is a tendency, let's say that you have on your desk sitting a calculator and right beside it a pencil, okay? There is a tendency for those two to come together and be attracted together, just like magnets. Okay, believe it or not. Okay, this is basically gravitational pull. However, it doesn't happen. You say, well, I've never seen a pencil rolling toward the calculator. That's true. And the reason is because the gravitational force is extremely weak. I mean, weak, extremely weak. So weak that it just doesn't happen. Okay? The most massive object that you see around you, really, is the one underneath your feet, the big giant Earth. Okay, so the big giant Earth overwhelms all those gravitating objects around you. So that's why things fall to the ground, because it is just, the biggest one is the Earth. And let me tell you how weak the gravitational force is. It is so weak you can actually stand up on the floor right now and you can jump and jump in the air for let's say a half a second. In other words, the muscle in your legs are actually stronger than the gravitational pull of the Earth. Okay, it's that weak. So imagine this giant Earth, the muscles in your legs are actually stronger than it. So imagine the gravitational pull between the pencil and the calculator. Extremely weak, negligible. You kind of just basically don't ignore it. So gravitational pull, it becomes dominating and significant, and we can observe it only at the astronomical level, at the level where you have a moon and an Earth, or a sun and the Earth, and so on, or a lot of stars in a galaxy. You know what I mean? So at astronomical level, the gravitational pull becomes dominating. But at the microscopic level, like a human level, we really don't observe it much, and we just happen to have the biggest mass. We live on top of that biggest mass, and that biggest mass is the one that we feel the gravitational pull from. Got it? Okay. All right, so that's basically what the formula is here. Let me give an example and show you how that works. Let's say I want to, this is just my own example, right? Let's say find gravitational pull. I think I spelled it wrong. Let me do it again. Gravitational pull, or when I say pull, I mean force, okay? Gravitational force between, let's say, the Earth. Oh, by the way, the symbol of Earth is like this in astronomy. That means Earth. And the Sun. It's a circle with a dot, okay? Here it is. Earth, Sun, Moon. I like to use those symbols. They're just kind of cute and convenient, you know what I mean? All right, so I want to find the gravitational pull between the Earth and the Sun. How do I do that? Well, I need to use the formula, this formula right here. Okay, here it is. So the gravitational pull, F, is equal to G, mass of the Earth, times mass of the Sun, divided by what? The distance between the Earth and the Sun squared. Why? Well, that's what the formula says. There it is. See that? All I need to do, and I can go to the back of the book. I believe you can find it at that appendix that I told you about in the beginning of the year. And if I look up the appendix, I can, at the appendix there is astronomical data. You can always also just look up Google, just say what is the mass of the Earth, mass of the Sun, radius of the Earth, or the distance between the Earth and the Sun, whatever you need. It will give it to you very, very quickly. But there is one on the table. So anyway, let me write them down for you. I already looked them up for you. So the mass of the Earth is equal to 5.972 times 10 to the 24 kilogram. Mass of the Sun is 1.99 times 10 to the 30 kilogram. And the distance between the Earth and the Sun is equal to 150 million. I have to look it up in Google. He gives me 150 million kilometers. What that means, well, million is 10 to the 6. So it becomes, if you analyze it, it becomes 1.5 times 10 to 11 meters. Okay, it has to be in meters, right? So now I want to calculate the gravitational pull using this formula right here, right? So let's do it. So that the force is equal to, G is 6.67 times 10 to the negative 11, and mass of the Sun, actually mass of the Earth is 5.972 times 10 to the 24th, Sun 1.99 times 10 to the 30, divided by the distance between them, 1.5 times 10 to the 11 quantity squared. Please use your calculator. Stop the video and use your calculator. Students make a lot of mistakes when it comes to scientific notation. As you can see, all of these are scientific notation. Please stop the video and calculate that by yourself with your calculator. Kind of teach yourself how to do it, and make sure that you get the answer. The answer that I got is this: 3.52 times 10 to the 22nd Newton. Make sure you get this answer. Well, unless I'm wrong. I have no idea. I did it once, and that's the answer I got, and I thought to myself, it looks correct. Here it is. All right? Let's hope so. I mean, of course, as you can see, the force here is very, very, very large, 22nd. Okay? But again, like I said, gravitational pull becomes significant only at the astronomical level. All right. Another thing, another concept that I want to talk about, and that is the concept of weight. We talked about weight before, but here weight in terms of gravitation. Imagine that you are, here is the Earth, right? I mean, right now you are sitting on Earth, on the surface of the Earth. So let me give you an example. Let's say here is the Earth, here is the radius of the Earth, and let's say that you are sitting right here. Here you are. I'm going to make you into a little block right there. That's you right there, sitting on the Earth. Is that okay? Now, this is the radius of the Earth. So how far are you from the radius of the Earth, from the center of the Earth? Well, practically speaking, you are about the radius of the Earth, right? I mean, you are far away by the radius of the Earth. So the distance between you and the center of the Earth is basically the radius of the Earth. You agree with me on that? So what I want to do, I want to calculate, here we calculate the gravitational pull between the Earth and the Sun. And I use this formula. Well, I want to use the same formula to calculate my gravitational pull from the Earth, between me and the Earth. Okay? In other words, between me here and the center of the Earth. You see what I'm saying? So that gravitational pull, F, is going to be equal to G, my mass, my mass, times the mass of the Earth divided by the distance between me and the Earth. Do you agree with me? The distance between me and the Earth basically is the radius of the Earth. Remember, the radius of the Earth is very, very large. Oh, I didn't show it to you. The radius of the Earth, it is equal to 6.38 times 10 to the 6 meters. Basically 6 million meters. Okay? So I'm nothing compared to that radius, 6 million meters. So practically speaking, the distance between me and the center of the Earth is basically the radius of the Earth. I hope you believe that. There we go. Make sense? This in itself is equal to what? If I would calculate this number, okay? Let's calculate this number. Here, let me show you. Let me calculate it, just for the sake of argument. So G here is 6.67 times 10 to the negative 11. What's my mass? Let's say my mass is 90 kilograms, roughly, okay? Of course, the mass of the Earth, I just showed it to you. 5.972 times 10 to the power of 24, divided by the radius of the Earth, which is the number you see above there, 6.38 times 10 to the 6, okay? Let's calculate that. You can pause the video and calculate it. Oops, but squared, right? I forgot to square it. So here we have, I'm going to calculate it myself as well, 6.38 are 6, and then squaring that, and then reciprocal times 5.97, 24 times 90 times 6.67, negative 11. Answer, I got 880, roughly, 880.4 Newton. There it is. Can you tell me the meaning of this word, this number? Well, the meaning of it is that basically me and the Earth are attracting each other with a force of 880.4. What is this force? Well, we have defined it before, and we called it the weight. That's basically the definition of the weight. What is the weight? When I say how much do you weigh, and you say I weigh 1,000 pounds or 800 pounds, what does that mean? It means Earth is pulling me with 800 pounds. Well, let me see what my weight is. Go back to chapter 5. Weight. Remember weight? W equals mg. Let me calculate my weight here. My mass is what? 90, I said. And 9.8. Let's calculate that. So that would be 90 times 9.8, 882 Newton. Do you see the difference? This is the mg. Do you see this number and this number right here? These numbers are actually exactly the same. Remember, we didn't get them to be exact because this is just rounding the mass of the Earth and the radius of the Earth. But if I would get exactly what the mass of the Earth is and what the radius of the Earth exactly is, I will get 882 here. Okay? In other words, the force that is pulling me when I'm on the surface of the Earth right now is nothing but the weight. So, in other words, this expression is just another way to calculate the weight mg. You'll get the same answer. You got that? So, in other words, I'm going to go back and I'm going to say the following. That means mg is equal to gmm Earth over radius of the Earth squared. Look at that. The masses cancel out. So I end up with something interesting. G equals G mass of the Earth over radius of the Earth squared. I get this remarkable equation. Now, if you would, this is your homework. This is your homework for today. You don't need to submit it or anything. But if you would plug in the value of G, the mass of the Earth, the value of G, the mass of the Earth, and the radius of the Earth squared, what kind of number are you going to get? I bet you you're going to get 9.8 or something close to it, meter per second squared. Okay? As a matter of fact, if I want to know the gravity, the acceleration due to gravity G for any planet or star, it basically G equal, same formula, G, the mass of that planet divided by the radius of that planet squared. That's how we find the G value of some astronomical star or a planet. I mean, how do we know Jupiter is 27? How do we know the moon is 1.67? And so on. How do we know the sun is 125, I think, something like that, 120? How do we know all these numbers? We know all these numbers from this one. We found out, and by other means, the radius of that terrestrial object that we're dealing with. We know its mass, and if we know those two, the radius of that object and its mass, I can find its G. See what I'm saying? So this is a very important formula. Make sure you box it. There is a couple of homework problems where you have to use this formula to find the G value of some planet. Okay, good. Now let me do a couple of examples before I do. I have actually two examples, yes. Example 6.9 and example 6.10. 6.9, I'm sorry, let me find it first. 6.9, page 166. It's right here. It says, in this example, we are going to calculate the weight of an object on the surface of the planet Mars and at a position well above the Martian surface. Suppose you are involved in the design of a mission carrying humans to the surface of Mars, which has a radius of, this is the radius of Mars, 3.38 times 10 to the 6, and a mass of 6.42 times 10 to the 23rd kilogram. The Earth weighs, the Earth weight of the Mars, the Earth weight, I read it wrong. Okay, the weight of the Mars lander, which is on Earth, okay, is equal to 39.200 Newton. This is the Earth weight. Remember, Earth, the weight is mg, so that the g here is g for Earth, not g for Mars. You'll have a different weight if you weigh it on Mars. Okay, so it's 39,200 Newton. Calculate the weight of the Mars lander and the acceleration due to the Mars gravity g at the surface of Mars, at 6 million meters above the surface of Mars, and so on. Okay? How do we do it? Let me write down what's given to us. There's a lot of numbers there. So he says the radius of Mars 3.38. So the radius of Mars, I'm going to call it m. I forgot what the symbol for Mars. 3.38 times 10 to the power of 6 meters. And the mass of Mars is 6.4. I'm looking at the hard copy here. Times 10 to the 23 kilogram. Okay? And he said the weight on Earth is, what is it? Oh, I have it here. Is 39,200 Newton. That's the weight on Earth. He wants the weight, the same weight of that lander on Mars. He says, what is it? Okay, and he wants also, okay, the part B. We'll come back to part B in a sec. All right, so that's basically what he's asking for now. All right, so how do we do it? Okay, I need to know what is the G value on Mars. That's the first thing I'm thinking about. So we know that the G value for any planet or star is this one, Gm over r, and I have everything. So the G value for Mars is basically G, the mass of Mars, over the radius of Mars squared. Plug it in. So I got 6.67 times 10 to the negative 11 times the mass of Mars, given to me above right there, 6.42 times 10 to the 23rd. It's going to be less because the mass, less than Earth, because the mass is less, divided by 3.38 times 10 to the 6 quantity squared. And when I calculate that, I will get I got 3.75 meter per second squared. That's the G value on Mars. So if I know the G value on Mars, what is the weight on Mars? Well, weight is equal to what? mg. For Mars, well, it's mg Mars. I just need to find the mass. Well, how do I find it? Well, he gives me the weight of that lander on Earth right here. So I have here, I'll just go here. So he said, given the weight on Earth is 39,200 Newton, and that's equal to mg for Earth. G for Earth, of course, is just 9.8. So in this case, the mass, remember, mass is invariant. It doesn't change for any planet or any star. So in this case, 39,200 divided by 9.8. And therefore, the mass of the lander is equal to 39,200 divided by 9.8. Answer, the mass is exactly 4,000. Right? And therefore, the weight of the same lander on Mars is mg Mars, so that'll be 4,000 times G for Mars is 3.75, is right there, guys. And that will be equal to 3.75. Answer 15,000 I got. And there we go. That's the weight of the lander on Mars. This is what astronomers do. They need to know what is the weight of that thing, whatever they're putting there. They need to know what's its weight. Okay. Now, that's the first part. This is all part A. Let me do part B. Part B says, so let me just go back to A. He said, I'm sorry, here, the Earth weight on Mars is this, and here, there we go. Calculate the weight at the surface of Mars. Okay, B, I'm sorry. At 6 million meters above the surface of Mars, what is the weight of it if it's at 6 million? Remember we talked about that before. The higher you go in elevation, the less the weight, because G kind of dropped down in value. You see what I'm saying? So how do I do that? How do I calculate something like that? Well, there are a couple of ways. So the second part says the following. Let me give you a picture. So here is Mars, right? He says if the Mars lander is in orbit around Mars, and he's asking, here's the Mars lander right here, okay? Of course, that's the radius of Mars. And now the Mars lander is at some height. I'm looking at the picture here. Here it is. You see the picture? Here is the Mars lander, excuse me, the Mars radius. And let's say that the lander is right here and above the surface, and it is 6 million meters above the surface. And he's asking for what is the G value. Okay, I mean, we can find the weight. If we know the G value, we can find the weight. You just multiply by the mass. That's easy. So I want to find the G value here. I mean, I know the G value on the surface of Mars by using this formula, the one we just used. What is it? Right here, right? So what if it is 6 million meters above? Not on the surface. Remember, this is R for the surface, radius of it. So what all you need to do is you add the height above the surface to the radius. In other words, the G value in this case becomes G times the mass of Mars divided by the radius plus that height, which is from here to there. Let me call it big H, and that's the radius, of course. So R plus H quantity squared. This is the radius of Mars. And that's the new G value. You got that? It's going to get weaker. So when we do that, it's going to be 6.67 times 10 to the negative 11 times the mass of Mars. I already forgotten it. Here it is. 6.42 times 10 to the 23 divided by the radius of Mars, 3.38 times 10 to the 6 plus, he said what? 6 million. You're going to add another 6 million here. 6 times 10 to the 6 quantity squared. All right. And now we're going to calculate this G value, the new G value here. All right. So I'm going to go ahead and calculate that with me. It's going to take me a little while to do it. So let's do it together. So your book does it completely differently. So let's see. This one is definitely an easier method in my opinion. And then I'm going to square that, and then reciprocal times 6.42 23. Answer. All right, I got the answer. I hope I got it right. I got the answer to be 0.48. Anybody got that? 0.48. No, let's make it 0.487 meter per second squared. Let me see if this is true. All right. So what is the weight at that? The weight on Mars at that point right here? Okay. What is that? The weight of the lander? Well, it's just mg. So in this case, the mass, we just got the mass. I forgot what the mass is. The mass is 4,000 kilograms right there, guys, right? So it's 4,000 times 0.487 and that will give me 0.487 times 4,000. Answer 1948. There we go. Okay. And let me compare it with what he got. Okay, he got the G to be the same as we did. Maybe he didn't calculate the weight, but anyway, there it is. Okay, this is the G value at that height. But anyway, you just multiply with the mass and you will get that. Oh, this is good enough. Okay, good. The next topic within gravitation, or subtopic, if you will, is satellite motion. Let me take up. I'm gonna explain satellite motion through the last example that I'm gonna work on, and that is example 610 on page 169. It's right here. Okay. He says, suppose we want to place a weather satellite into a circular orbit 300 kilometers above the Earth's surface, right there. Okay, this is the Earth right here, this big sort of solid circle here. And then the Earth satellite is right here, 300 kilometers above the Earth's surface. What speed, period, and acceleration must it have? Okay? And then he gives you the data that you need. All right? How do we do this one? Okay. Example 6.10. So what you have in here is the Earth right here, and here is the, it's highly exaggerated, of course. I hope you understand that. So here the height here is 300 kilometers, and of course way down there this is the radius of the Earth. And here is the satellite here, and let's assume it's going this way. Okay. And the question is, what is, he said, what is the speed, velocity, period, and acceleration? So he wants, what is the speed, period, and acceleration of it? Okay. All of that. All right. How do we do it? Well, because it's moving in a circular way, guys, that means there is a centripetal force on it. What is the centripetal force? What is causing the object to go around in a circle like that? The satellite, or the Earth going around the sun? Well, it's the centripetal force. What is that centripetal force? In this case, it's not the friction like we did last time. It is the gravitational force. Okay? In other words, the reason, let me just digress a little bit. Here is the sun, right? Here is the Earth going around the sun. Here is the Earth. This is Earth, okay? Going around the sun. Here is the distance between them. The centripetal force here between the Earth and the sun, that centripetal force, F sub c, is nothing but the gravitational force. So in other words, the centripetal force, the gravitational force is playing the role of the centripetal force. It is the one that is causing it to go in a circle. And that's exactly what we have in this case. You got that? So if I want to calculate the velocity, the period, and acceleration, all I need to do is to set up my formula in the following way. What I have is that the centripetal force, F equals ma. Let's just start with F equals ma. Of course, the m here is always the orbiting object. It's not the object that is stationary like the sun. It's the orbiting of it. For our case here is the satellite. I'm going to call it S sub S for the satellite, just to remind myself, even though it may be not necessary. Anyway, and then you have the centripetal force, which is the gravitational force, G, mass of the satellite, mass of the Earth, divided by the distance between them, which is what? The radius of the Earth plus that height squared. What's the height that I'm talking about? This one right here. So you're going to add this height right here plus the radius. The radius is right there. That's the radius right here, right? That's the radius of the Earth plus that height. So the total distance from here all the way to there, oops, I'm sorry. The total distance from here all the way to there is basically r plus h, where r here is the radius of the Earth. You got that? So, and this is equal to the mass of the satellite times a sub c, okay? Now, he's asking for, look what he's asking for. Find a sub c, tau, and v. Well, I can find a sub c for now. See, the mass of the satellite, he didn't give me the mass of the satellite, did he? He probably didn't give it to me. Let me look. He didn't give it to me, and I think he didn't give it because, as you can see, it's going to cancel out. So in this case, a sub c is equal to g mass of the Earth divided by radius of the Earth plus the height quantity squared. All I need to do is just plug in those numbers. So that's going to be 6.67 times 10 to the negative 11 times the mass of the Earth is given to me, 5.98, this is from the problem, times 10 to the 24, divided by the distance. The radius of the Earth, as you know, is 6.38 times 10 to the 6, plus the height. He said what? 300 meters right there. So that's 300,000 meters. So that's 3 times 10 to the 5th, correct? So that will be 3 times 10 to the 5th. All of that quantity squared. And then when I calculate all of this, okay, when I calculate all of that, I will get the number. Well, let's calculate it. I mean, I have the answer in front of me, but I want to calculate it. Let's calculate it together. That's what I'm saying. So let's do that. 6.38, 6. And then I'm going to square that, reciprocal, times 6.67, negative 11, times 5.98, 24. Answer, I got 8.93. 8.94 actually. Okay, your book got 8.95. I'm reading the hard copy. That's good enough. So anyway, we have 8.94 meter per second squared. There we go. That's a quick way of doing it. Now, okay, so now he said, what is the velocity? Well, I know that a sub c is equal to what? V squared over r. Of course, r here is r over a plus h. Let me put a small r, such that r is r for Earth plus the altitude, plus that height. You know what I mean? So I need to include all of that. So in this case, the velocity is the square root of a sub c times r. Okay? So that will be a sub c times this plus the height. You see what I'm saying? So let's do that. So it becomes, I got a sub c to be equal to, I hope you're taking notes so you can look at it up. So it is 8.94, is that right? Times the radius of the Earth, 6.38 times 10 to the power of 6, plus 3 times 10 to the 5th, is that right? And then we put them under the root. Let me calculate that again. So I have here 6.386 plus 3/5 times 8.94. Take the root of that. Answer, I got 7727. 7727. Your book got 7730. Again, it's all rounding. I'm just going to stick with my answer. I got 7728, let's just say, because it's 7.8 meter per second. Okay, there we go. That's the velocity. And then the next part, he said, what is the period? Well, what is the period equal to? Well, we know that the velocity is 2 pi r over the period. So therefore, the period is 2 pi r over the velocity, or for our case, 2 pi r Earth plus height over the velocity. And I'll leave that up to you. I'll leave that to you to calculate it. And the answer that the book has for this one is roughly 90 minutes. He converts it. I'm not going to give you the second. You can calculate that. So it's approximately 90 minutes. That's the period. And there we go. This is how we do it. Okay? Okay, good. 6.10. I think I am done with the chapter. So maybe I have, let me do a couple of problems from the book. I have number 44 and maybe 50. Okay, I'll do number 44. This one, the homework, there are 10 problems, but I promise you I think all of them are easy. 44 maybe it's the hardest, but it's not even hard really. I don't think it is. Anyway, I'm going to do number 44 and 50. Okay, these are homework problems. Okay, page 177, 44. Right there, it says volcanoes on Io. Io is one of the moons of Jupiter. It says Jupiter's moon Io has an active volcanoes. In fact, it is the most how do I say this? Volcanically, I'm sorry, I can't pronounce this word. Active body in the solar system that eject material as high as 500 kilometers or even higher above the surface. Io has a mass of 8.94 times 10 to the 22nd kilogram and the radius of 1,815 kilometers. Ignore any variation of gravity over 500 kilometer range of the debris. How high would this material go on Earth if it were ejected with the same speed as on Io? Okay? Piece of cake, right? Right. Okay. All right, let's do it. So let's write down what's given to us. Here it says volcanoes, volcanically. I think, there we go, now I'll pronounce it, volcanically. Volcanoes, sorry. On Io. All right, so what we have, the height that is reached is 500 kilometers. The mass of Io, I'm going to call it m sub I, is 8.94 times 10 to the 22nd kilogram. And then the radius of Io, always write down the given. Try to make a diagram if possible. I don't need a diagram for this one. I don't think I do. First thing I need to do, I want to find G on Io, the G value. And we know that G value is what? G m sub I over r sub I squared, correct? Just plug it in. So I have here 6.67 times 10 to the power of negative 11. The mass, 8.94 times 10 to the 22nd divided by the radius, 1815 times 10 to the 3rd meters. Remember, it says kilometers here. Remember that? So look at that. So I have to multiply by 1,000. And when you calculate that, I'm just using my notes here. I already solved this problem. You will get 1.81 meter per second squared. So this is the G value on Io. It's not much. That's almost equal to the moon, really, the G value. The moon is 1.67, I think. Our moon. Okay, there we go. Now, he's saying assume that this G value does not change with height. Okay, so it doesn't change with that height. All right, fine. He says, what is, look at that. He's saying, how high would this material go on Earth if it were ejected with the same speed as an Io? Got it? So I need to know that same speed. I need to know the speed. What is the speed on Io? I got the G value over here. In other words, what I'm going to do, I'm going to be using free fall kinematics, but free fall kinematics on Io to find that speed, because I'm going to take the same speed and I'll apply it to the Earth. You got the plan? All right. So I'm going to use free fall kinematics in this case. In other words, here I am on Io. Here is the surface. This is Io. And let's assume the volcano is, I am throwing something. So I'm going to throw that thing all the way here. It's going to fall, right? I want to know that initial speed. Of course, the final speed here is 0. Okay, and the G value here on Io is equal to 1.81. That's the G value. So I'm going to use free fall kinematic to find out what V0 is. The second equation will be the best suitable one. So that's going to be V squared equals V0 squared minus 2GY. Y is what? Is the height. And this height is given to me, actually. Here it is. It's this one, the one I call H. Let me go back to it. Let me call it Y here, if you don't mind. All right, H, Y, whatever. That's the height right here. 500,000 meters. So there we go. So all I need, of course, the maximum height, the velocity becomes 0, and I want to know V0. So V0 is nothing but the square root of 2GY. The G here, of course, on Io. And there we go. So I have here 2 times 1.81 times the height 300,000. I'm sorry, 300 or 500? I'm sorry. Let me go back. 500. I beg your pardon. 500. And then I calculate that. So when I calculate that, I get 1345.4 meter per second. Okay, so the speed here, initial speed, is 1,345.4 meter per second ejected. Okay, now I go back. He said, what is how high it will go on Earth with the same speed? So I use the same free fall kinematic, but this time for what? For Earth. So now on Earth, I can just say on Earth. So here is my free fall kinematics. 2G on Earth. I'm going to just remind myself, put that thing there for Earth. And of course, it's going to reach 0 speed at the maximum height. And this time I'm solving for Y. Do the algebra, you're going to get this. Plug it in. So V0 squared, I just got it right here, 1,345.4. So that's 1345.4 squared divided by 2 times 9.8. And when you calculate that, I got 92.4 kilometers. Again, this is in kilometer, not meter. And there we go. Okay. In other words, on Io, it goes all the way 500 kilometers right there. See that? On Earth, it goes only the same speed, same material, same mass. It goes 92, only 9. Why? Because gravity on Earth is much higher, 9.8. On Mars, on Io, is only 1.8. You got that? So that's the story. Okay, good. The last problem I want to do is number 50. 50 is kind of a cool problem. It's actually pretty easy as well. Let me go over it, and then we'll call it a lecture. I should do it for today, I hope. Right there, here. Make it bigger. There we go. Right here. Okay. Oh, it's level 1. Okay, I didn't know that. Okay, it says the star Rho Cancri is 57 light years from Earth. Okay, I don't think this 57 is a big deal. Is important for our problem. Anyway, so we have the star Rho Cancri is 57 light years from Earth and has a mass of 0.85 times that of our Sun. Okay, this is a star, and its mass is 85% of the mass of the solar mass. We call it solar mass in astronomy. Okay, a planet has been detected in a circular orbit around Rho Cancri with an orbital radius of 0.11 times the radius of the Earth's orbit around the Sun. Okay. Question: what are the orbital speed and the period of the planet Rho 1 Cancri? I guess this one is part of the name somehow. Anyway, there we go. So that's the question he's asking for. Not bad. Let's write down the data first. So I have a star, Rho Cancri. The distance to us is 57. I don't think this is important, so we're not going to worry about it. The mass of the star, I'm going to call it M sub star. Is that okay? Like that? Is 0.85 solar masses, the mass of the Sun. You get that? See this notation? Okay, and the radius of the star is equal to 0.11, the orbital radius, that is the distance between the Earth and the Sun. That's what he says. Okay, and part A, he says, what is the orbital velocity? Basically the V that we have been calculating. And B, what is the period? Okay, so we have something like that. Let me show you a picture of what it looks like. So here is the star right here, and this is the parent star, and here is the planet, and it's been observed to move with the velocity, and then this is the radius right here, the radius of the orbit. I'm trying to erase that thing, just bear with me. It will not erase. There we go. Okay, and this is the mass of the star here. Okay, so how do we find the orbit, the velocity of the orbit? Well, one way to do it is we start with the F equals ma. So this would be G, mass of the star, times the mass of the orbiting body, this m right here, divided by the distance between them squared, equals the mass of the orbiting body times A, and A is what? V squared over R star. Okay? So here the mass of that's why he didn't give you the mass of that planet, the exoplanet that he's talking about. But he gives you the mass of the star. And then this part is canceled with this part. So basically the velocity becomes equal to G, mass of the star, divided by the radius of the star. You can actually box this equation and actually use it all the time rather than going through those 3 steps instead of saying. So anyway, there it is. That's the formula. And then we just calculate it. We just plug in the numbers in there. So I have here, I'll do it here. Everything is given to me. So I have here V equals to 6.67 times 10 to the minus 11. The mass of the star is 0.8, the solar mass. I think you can calculate that yourself. So 0.85 times the mass of the Sun, you can look it up, divided by, he says, the radius of the orbit is 0.11 times the radius, or the radius of the orbit between the Earth and the Sun. Okay, again, you can calculate that and get that number. Okay, shouldn't be difficult, I hope. And then he wants the period. Well, what is the period? Period is 2 pi r divided by the velocity, correct? Remember, we said the velocity is 2 pi r divided by the period. So the period is that. I already got the velocity right here. You can plug it in there, and then I have everything else, and I can find the period. Not a difficult problem, I hope. Okay. I think I'm going to stop here. Please let me know if you have any questions about this chapter or anything else. And have a good week. Bye-bye.